Okay, good afternoon all. And thank you for coming along to hear the Irish guy with the weird accent. So you can put up with me and stuff this afternoon. What am I here to talk about today? What are we going to cover? Well, I want to talk about code. But probably not code as you normally think. What we normally think about code is derived from the original code, which I want to talk about today. And look, since we're in Italy, we're going to look at, well, what's the code to make good coffee? Right here, you should know how to make good coffee. Some parts of the world make terrible coffee. I suppose it's just like, if we're going to make source code or whatever, we want to do it well. We want to kind of do it nicely. So is this the correct protocol to make coffee? Is that how you would go and do it? If you were stuck in your hotel room and you don't have a means, but you have an iron, and you could probably bring a coffee pot with you. Well, since we had no coffee after lunch, that's what I was kind of feeling like doing for a while, because I think I needed some. Now, but what I'm really going to talk about here today is protocols, because protocols are steeped in code, and this should become quite obvious as I kind of go along. I'm going to kind of put out an interesting question to begin with, and I'll revisit this at the end, because in some ways I think protocols are one of the most significant things that we have discovered and started applying as humans, and it happens at a very, very low level right through to achieving some quite extreme and amazing things. Like if you've been following the news this week, you're probably well aware of this phenomenon, one of our first photographs ever of a black hole, and the great work by Kini Berman and her team that achieved this. But to achieve this, it's not just one individual. One individual can cook their coffee. This took many people working over a long period of time, building on knowledge from before, which is kind of really amazing what we can do as humans when we build on stuff that comes from before. And let's look at a bit of what is a protocol and how does this apply? Because we're probably all here as techies. Let's sort of wind it right back. Now, as a protocol, I like to go to the dictionary to find out, well, what's the way to define stuff? I'm dyslexic, so I like to look things up so I understand what I'm reading with, what I'm doing with, because one of my kind of bugbears is the fact that we give things terrible names in software all of the time. But let's look at protocol. What is it? Well, it's a code. That's where I'm saying to begin with. But it's to do with treating with things with a strict etiquette and precedence. So etiquette is the behavior by which we do things, and we'll go into that in more detail. But what's really kind of important for me in computing, particularly in concurrent and distributed systems, is precedence. Order and time starts to really matter, and we'll see this as we kind of go forward. We will often hear it shown this way, where we're talking about a set of conventions, and these conventions govern things like the treatment and the formatting of data. Most people just think the formatting side of things, and this is where we often misuse words, particularly. Formatting is quite a small part of what a protocol actually is. So before I get right into the technology side, let's take it right back, because protocols have got their root in evolutionary biology. And this is where we sort of start developing these things as humans. Like, go right through to a thing like facial expressions. So Charles Darwin, people may know of his work on origin of the species. We kind of know this all about evolution. But one of the other interesting pieces of work he did was how us as humans have an inbuilt, innate sense to understand certain emotions, independent of language, independent of culture. Like, for example, we understand disgust, we understand joy, we understand shame. Some of these things, these are really built into us and hardwired. And even if someone has never learned language, we still understand these things. There is examples in human history whereby people had a feral upbringing and they never even were taught to speak, yet they understand some of these really basic things. And it starts to really matter, because this is how we start to communicate. These are protocols of interaction. And things like disgust drives a lot of how we will do or not do things. And we build on this, and I'll come back to it in a little bit more detail. We've evolved on this, and so we now have terms like etiquette and manners. But again, these are just building blocks of protocol. Etiquette, originally from Old French, around about the time of Louis XIV. Etiquette actually means little card or little note. At the Palace of Versailles, all the keep off the grass type things that we'll often hear, that's where it started. It was little notes saying, you're not allowed to go walk on the grass at Versailles Palace. And so this was sort of teaching people in court how they should behave, what they could do, what they could not do. We evolved this forward into modern day manners. But if we break it back, if you actually look at the study of some of manners and etiquette, it comes into 3 groups. First group is known as the hygiene manners. And this is all typically about how we avoid disease. This is where the roots of things like disgust come from. We see something that's dirty, we'll express disgust, and we'll stay away from it. This protects us from disease. This also kind of applies in code, and I wish we'd do this more often. Like, I've seen a lot of JavaScript, and I often get that feeling of disgust when I look at it. It's pretty nasty and horrible. I've been programming for a long time, used a number of different languages, and some languages have got to go so far. I kind of wonder why. Did people not sort of register their own inbuilt, hardwired human behaviors and just show enough disgust that we stop these things early on, and and the things that are nice and good, we should bring them forward. But so we have this across all societies in the world where we build on that. The next layer up is courtesy. And we build societies based upon courtesy, and the whole point to this is it's not about the individual. The society is more important than the individual. A good example of this is sometimes the leaders in many societies will eat last, and that means others get to eat first. You're showing that actually you are less important than society as a whole. We see this even in other species, like wolves will do this. The leader of the pack will eat last, will go at the back when they're moving between places. And that's to show that actually the group is more important than the individual. So we kind of build upon this. Third layer is what are known as the norms. And so this is where a group or society all behave in a certain way. And this is the root of identity. And by all behaving in the same way and showing the same sort of manners to each other, we then have trust. Trust allows us to do things more efficiently, because when you don't trust someone else, you have to put certain protocols, certain behaviors in place, and that slows things down a little bit. So we kind of work on all of these, and some of these rules will actually interact with each other and will break things down. So for example, the hygiene things is we know about sort of social space, personal space, and intimate space. We only let people that we trust into the various levels of that. And so we'll actually break some of the lower level rules to achieve some of the higher level rules. But we kind of got to respect those, and that's how we get society to function. Like, to go through to one of the most sort of sophisticated and most developed ideas of protocols is you actually look at the military. So the military have got an idea called rules of engagement. And it's all about what is acceptable when you go to war. And this becomes important because going to war is an absolute last resort, and it's something as humans that we just shouldn't treat lightly. And as a result, we have a whole body of laws around this that encode our protocols. We look at it through certain terms. Like, one of the ones is we look at good conditions to succeed. I've seen a great speech by a guy called General Mike Jackson, and he talked about the purpose of war. And the purpose of war, to him, was not about crushing your enemy. It's not about beating them. It's about changing their mind. And you use warfare as an absolute last case resort to change mind. And he was very effective in a number of different realms because he had different thinking about this. And there's a lot less problems afterwards. And we kind of learned from this. There's actually Latin terms if you start reading the laws, like just ad bellum, just ad bello. First is to deal with what are the rules around going to war, and the second are the rules that you must take part in once you've gone to war. If you break these laws, this is the fundamental difference between being a criminal and being a soldier. For example, murder and being a soldier are very distinctly separated by the fact is, are you in a just war or not? And this is where we get certain rules around this. So we kind of think about this, and it's all about, like, how do we do things proportionally? How do we behave well? From the second group, like, what do you do when you go to war? Well, one of the things is you must be proportional. So, for example, if you're a superpower and you've got nuclear weapons and somebody attacks one of your ships, you don't go and nuke their capital. That is not acceptable behavior. It has to be proportional. So this is kind of an interesting history through this. I find it a fascinating subject to study because I think there's a lot to learn from it. But we can take it into computing. And as an industry, we're very young. We're sort of working this out as we go. So our protocols are not as advanced as they are in other industries. So for example, if you're a doctor, there's very strict protocols around how you should behave, how you should do things. Like, if I perform surgery, if I go into surgery, I must wash my hands. That is a protocol that that profession now has. If you don't do that, you could be disciplined by your professional body. Kind of interestingly, have we got parallels in that? I would kind of argue, if you're writing any software professionally, if you did it without tests, you are not respecting good hygiene. Think about it. So you're basically saying, you're just going to take the risk and you're going to give this to someone else, like a surgeon not washing their hands. So if we're going to grow up as an industry, we have to get our own protocols and how we behave and act a little bit differently. So let's get into the techie stuff. This is kind of where we're probably wanting to explore in a bit more detail and make it a bit more concrete. So concurrent distributed systems, we want to look at how protocols interact. How they interact is the really interesting bit of where protocols come from. And what work is there in this space? You may have heard of the IETF. This is where probably the largest body of protocols get documented that we use. And our internet is all based upon protocols that are defined here. We can go and look them up. There's also some quite cool stuff there. Like on the 1st of April every year, they bring out a kind of fun protocol. Here's one back from 1998, which is a protocol for how to control a coffee pot. Now, we need coffee, it's kind of important. And this is kind of fun stuff, and I love some of the cool bits that are in this, like they have defined an error code, 418, which you respond as, sorry, I'm a teapot, I'm not a coffee pot instead. This is kind of cool. But some of these are really informative as well as being fun. I actually recommend that you go back and read the 1st of April protocols that are defined in the IETF. This is one of my favorites. It's called the Holy War and the Plea for Peace. If you ever didn't understand about representing integers on the wire, like big Indian and little Indian, you may have heard these terms. This is the best description you'll find anywhere, and it's actually really good fun. Like, for reference, why is it called Big Indian and Little Indian? If you've ever read about Gulliver's Travels in Lilliput, they used to argue about which way you eat your eggs when they're boiled. Do you break the big end or the little end first? And one group was in the big end, another one was into the little end, and those are the big Indians and the little Indians. And this is where we define integers, and that's the history of some of this sort of fun stuff. So you kind of wonder, what am I doing when I'm using Java byte buffer and I'm setting order and it's big Indian? That's where this stuff comes from. That's kind of interesting, fun, and it explains it really well. There's other cool things in here, like how do we use pigeons to represent communication between things? And I love the bits like avian carriers can provide high delay, low throughput, and low altitude service, but they've got built-in collision avoidance. So it's kind of, if you're a networking geek, this is all actually quite amusing sort of stuff. This was updated over time, so we added quality of service to avian carriers, and recently we brought it up to date for IPv6. So this is kind of fun stuff. So this isn't all just boring stuff to read. There's some cool stuff in there as well, and there's lots of other really cool examples there. There's some pretty bad examples too, but there's some pretty good ones. Now what's kind of interesting is how do we document our protocols? It's an interesting question. Like if you go to the IETF stuff, it's just text. It's not complicated, it's not fancy diagrams, but it describes things incredibly well. And I think this is a really important thing that as we're going to grow up as an industry, we have to get better at. I hear this debate a lot, APIs versus protocols. I think most people don't understand this. They talk about API design. That, to me, is such a small component of how we design interactions with systems. It's very one-dimensional to look at an API. I think a protocol is much more powerful. Let's have a concrete example. What's the protocol for using a file? Well, I like to describe this, and a few other people have taken a similar approach. It's used like regular expressions as a way of defining something. So remember the precedence part of a protocol? It's actually really important. What's the order in which you're allowed to do things? APIs don't give you that precedence. They don't tell you the order. So if I want to use a file, I've got to open it, then I can follow it by 0 or more operations of write or read, then follow it by a close. So that gives me a clear order in which I'm going to use something. It tells you a lot about how someone should interact. I would sort of tempt people to think about, whenever you're going to design the next component of your system, don't just think about the API, think about what the protocol is and spend just a little bit of time documenting it. So it can be as simple as you write out the precedence and then you just document what each of the major features are. This is just a little bit of text. It will really improve the design of your system if you start thinking about this. Because once you've got this, you can start to make things much more robust. So think about it as like, if you're dealing with any distributed system, or concurrent system's just the same, think of the events that are going to happen to the system. What are those events? How are you going to react to them? What sort of treatment are you going to give them? What is the etiquette under which you're going to behave whenever you deal with those? And we sort of think about, well, what are the preconditions for doing that? What are the post-conditions for doing that? What are the invariants for doing that? Like, we don't like people coming into our personal space that are not friends. So the precondition is you've got to have a relationship before someone invades your personal space. These sorts of things. Like, we learn this in the human world. We get peeved off by people who don't respect these things, and then we show our disgust, we show our displeasement. But we don't do this in software so often. We've got to think a little bit more about it. And kind of really importantly, is start thinking about what can go wrong. Well, this is something I've kind of learned over the years, and actually in recent years has been drilled in to be much more extreme, where I work with a guy who's really good at this sort of stuff, and he'll often say, no, really, what can go wrong when you're designing something? Because we so often don't think about this. So at one level, it's like, what if I don't get a return from this? What if it takes too long? What if something happens out of order? Like, what are you going to do? You don't just forget about it. There's some fascinating studies out there that show that actually the majority of P1 incidents where a system goes down in production is usually because of poor error handling. It's something we put around to later. But it starts to become really important. And I think there's a bigger question about that, because it kind of shows our immaturity. And then this shows in some of our social stuff, like our complete lack of ethics in our industry is also a great example of this. We're just trying to work this out. It's kind of like doctors in the 1800s, like before they got proper ethics with how they dealt with patients. Now we're kind of having to learn the impact of what we're doing. So let's make this a bit more concrete with a real example, which I think is kind of a great way of showing how to deal with something from a protocol perspective. Multicast is a really interesting protocol for sending messages on a network. We're going to send a message from one source to many receivers. It's got some implications to that, and some cases where it becomes an important way to design. So let's say if I had a chat application or some sort of whiteboard that they've got many observers of it, and occasionally some are interacting with it, but lots and lots of readers. Everybody needs to see every update. Well, if we do this with Multicast, we can send out messages to everyone, and now we've got to deal with some issues. Some of those messages are going to get lost. What can go wrong? They get lost. They arrive out of order. You may not get them. You may get them multiple times. So we end up building protocols on top of that. Like in TCP, it's got built-in protocols for dealing with that, but it's only one-to-one. It doesn't scale. One of the things they do is for packets they send out, they send back acknowledgements. Based upon those acknowledgements, you can then send more. It keeps things in order. We deal with the loss. But if we try to scale up to a larger point, we can't do that. So we can't start hacking everything. A better approach is to knack when things go wrong. So you send a negative acknowledgement to say, I never got that packet, please send it to me again. It's a kind of nice way to go. But you do that, and it's actually quite a naive approach as well, because you can then get a thing called knack implosion. Because whenever you start losing stuff, loss tends to be correlated. So you happen to overrun a buffer on the sender, you go to send something out, it doesn't go to anybody. So everybody's listening, and then they're thinking, okay, I never got the packet, I'm going to ask for it again, I'm going to send a negative acknowledgement. So everyone sends her a negative acknowledgement in. That's a lot of negative acknowledgements going back to the source. The source then responds to each of them individually, sending out the packets again. That becomes even more traffic, whilst we're trying to send traffic in the first place. A lot of those will get lost, so then you'll send more knacks for that, and you get into what's known as knack implosion. It becomes a complete mess and doesn't scale. So if you design network protocols, you start to realize a lot of these sorts of things start to happen. In the 1980s, the internet was failing. So I happened to have an internet account back before the web existed. I was one of the people who used these things sort of back when I was in school and university in the 80s. This was a kind of interesting time because the network started to fail and people didn't know why. All the computer scientists kind of didn't get it. And we got rescued by some physicists. So in particular, Sally Floyd and Van Jacobson, they're a couple of physicists working at CERN. They realized what was going on, and they described congestion collapse. They put protocols into TCP that solved this problem, and this is why we have a working internet these days. So it kind of got further. Sally also did another really interesting piece of work around multicast. And she produced this paper, the Reliable Multicast Framework. And it was a way of sending out data over multicast for, like chat, for whiteboards, for things like that. And it used a negative acknowledgement protocol. But there was a way of dealing with the problem of the NAC implosion. So rather than just sending a negative acknowledgement straight away, whenever something happened, what you do is you set a random timer. That random timer would go off within a certain window. And when the random timer went off is you would check, had the packet arrived, had somebody else sent the packet in the meantime. If not, you sent the negative acknowledgement, that went to the source would then send the packet. And because you've got a random distribution, it spreads it all out so everybody doesn't do it at the same time. It also has a nice impact is that if one in the group sends the negative acknowledgement, everybody else gets the retransmission of the packet, so you get the benefit. So you only need one NAC to happen. But you have no central control, so you just use a random timer to do this. That works really nicely. It's actually interesting, no central control. It's a protocol based upon coordination and some rules. But when you look into it in some detail, if you use normal distribution, you get a big clumping of a cluster, and still you can get a little bit of NAC implosion that can possibly happen. So let's look at that in a different way. Here was another paper that came out a little bit later, looked at the same problem and thought, rather than use a random distribution, how about if we used an exponentially weighted distribution and we knew the size of the receiver group and we knew roughly the round trip time, we could skew the distribution so the majority are pushed back to later in time, but enough or have a high probability of happening early on that you actually reduce latency and reduce network traffic. And it worked really nicely. So thinking about the protocols of interaction, notice in all of this, there's no central control. There's no one dictating what happens. It's just a set of rules, but if everyone plays by the same rules, it works really nicely. So thinking about the protocols of interaction. So that's kind of a simple little example. Like, why do I know about these sorts of protocols? Well, I work on a messaging system, and these are the protocols we use internally. We don't use central control. We don't use brokers. Everything's peer-to-peer. Everything's equal. And you know what? It scales really well and performs much better than broker or central control solutions. I think this is part of our problem as an industry. I think because many people who've gone into tech, quite often very young in their career, not really guided by people who have been around and dealt with difficult problems, it becomes a very naive sort of central individual-focused approach to it. They don't think in the large. They don't think in the societal terms of how do we collaborate at a larger level and do amazing things. Like, I'm not at all surprised that the likes of these protocols come from physicists who were collaborating on a global level to solve some really hard problems. And by doing that, collaboration was a natural way they were thinking. So it changes the dynamics of some of this. And these sort of things are going forward in kind of new and interesting ways. So what should we focus on from a protocol perspective? Well, there's lots to it. So we can look at versioning, we can look at layering, how do we handle feedback from basic information theory, sequencing, batching, all of this sort of stuff, and then important things even like trust and privacy. I'm not going to go into all of that. I'm going to pick off a couple of examples just to give you a flavor of kind of some of the thinking in this. So kind of first up, like, how do we encode stuff? How do we put stuff on the wire? Because the formatting is one of those points, is what most people think about. Well, we've kind of done the quite naive thing of we put things into text. Like, so if I can leave you with one thing to think about going away from today, if you actually cared all about wasting energy and trying not to, please stop using text-based protocols. They're one of the biggest wastes of computing power and energy we have in computing today. I get to measure lots of systems, and so often the business logic is almost a rounding error compared to how much time we spend in frameworks and layers and dealing with sort of text-based codecs in sort of JSON and XML and JavaScript and all this stuff that should be showing the disgust again at this stage. And you kind of think, well, why am I talking about the binary stuff? Is it possible? People say it's too hard. Well, if you actually look at most of the IETF stuff, like we've gone from, we'll end up drawing all these sort of pretty pictures in ASCII art. You kind of get good at doing cool stuff with ASCII if you sort of work on this sort of space. Even in the IETF, we've gone from doing stuff with text-based protocols through to binary because we realize the limitations that's in there. So we try to get a bit better at this. Versioning is another fascinating thing because when we start dealing at any level of scale, we can't upgrade the whole system at a time. It just doesn't become possible. So we got to know at what layers we're dealing with what versions and what identity of what. For the protocols themselves, is what conversation am I actually having? That becomes a kind of fundamental question. We should build this in so we can very quickly work this out when we're looking at network traffic, when we're looking at interactions. Like the messages themselves, how have they been encoded? How can we extend that over time? So we can add new fields, we can add different ways of dealing with stuff. So it gets more efficient and we deal with new features without breaking backwards compatibility. Again, we can put this into it. One of the ones I find that is least often thought about, but actually one of the most powerful, is how we even version state. Most people don't think about this as what state is the system currently in? If you've got a concept of a version of state, especially in concurrent or distributed systems, we can get away from many of the ABA and more complex problems that are in there. Like, this is an example of a problem I've faced myself. So I've developed a number of concurrent queues in my career. And as I've worked on them, I've sort of taken lots of ideas from the past. There's some really nice work by people like Leslie Lamport. There's other sort of bits and pieces that have kind of come on over the years that have got better and better. But as you start combining them, you start dealing with some of the complexity, you start to realize there's certain cases start to get quite hard. And one of the most difficult one is a many producer to a many consumer queue. Now, I implemented one that was taking the basic ideas from Lamport's work and I added to it and it got better and better over time. In the end, I had an implementation that was pretty fast. It worked quite nicely, but I found that there was bugs that used to appear occasionally. And so eventually we dug into it, found out what was going on, and there were some edge cases around full and empty of queues that we had to deal with. I ended up sort of fixing some of the problems that were in there and eventually refining it to it would be correct. But it wasn't elegant. It was very complex, very difficult. And then I thought, I want to look somewhere else. There's got to be better solutions. This is where I find Dmitry Yukov's work on 1024cores.net, where he had a really nice algorithm for the many producer to the many consumer queue. And the insight that he had, which I felt was much better than anything I've seen before, he versioned all state. Everything had a version. And so whenever you had these boundary conditions of the full and empty, and you're wrapping around and reusing slots in an array, you didn't have the problem because everything had a version. You were sure that the slot you're using at that instance in time, maybe the same place and space, but it was a different version in time, and that way we could deal with it. So it just became really obviously correct when you looked at this. So it was kind of beautiful. But also another really interesting thing that this guy points out is any design that requires a many producer to many consumer problem, you've got your design wrong and you need to back out. And I think that's from the person who produced the best algorithm ever in that space to then turn around and say that is actually quite informed because we make things far too complex. Like the state versioning shows up in lots of other places where it's done better. Consensus algorithms are another good example. If anybody's worked with Paxos or some of the early versions of virtual synchrony, Ken Berman's work, whatever, it's all very complicated. And then recently we got some breakthroughs with papers like Raft. But for me, the real breakthroughs, and sort of, this is not just the Raft stuff. I think Barbara Liskov also deserves a lot of credit for some of her work in Bluestamp replication, where everything gets versioned. And with everything being versioned, it becomes so much easier to reason about what's going on. We can see when the state is correct and when the state has changed. So the whole ABA problem, something that looks like a state that you've seen before, but is not the same state. It's just the same shape as the previous state, which is so easy to make a mistake with. So these sort of things help, and they help a lot. Sync versus async is a huge debate. I see it brought up a lot. But let's break it down and run through it quite quickly. If your two systems are going to communicate, if you're going to have synchronous communication, you send a request, then we get a response. You send another request, we get another response. Blah, blah. It's pretty simple in how it works. This is how most people design their services, and it's kind of driven by REST and HTTP. So we're actually using our document fetching protocol as a way of designing our applications. I don't realize how broken that happens to be. For me, I've just found that really quite weird. Now, if we increase latency, so things become further apart in space and time, what's the implication of that? Well, it takes longer to get your response. Now I can only do what I want to do 3 requests before I can only get 2 requests done in the same amount of time. This becomes an interesting problem when we start thinking this way. And what's happening whenever this sort of thing occurs? We're having to suspend threads. So we get a lot of bureaucracy by going into our operating system, suspending a thread, waking it up when we get the response later. We use the stack as a means of managing our state, which is a bit complicated and heavy way to do that. If we do it in an asynchronous manner, same situation, we send a request. We don't wait for the response, we send another request. We send another request. And then we can start getting the responses. So we greatly compress the time. And as we move to things like mobile networks, where the latency is higher, this starts to become much more of an issue. We're getting more and more bandwidth, but latency we're not going to overcome. We're facing speed of light issues that you cannot work around. We end up increasing the latency. What happens? Doesn't get any worse, really, that much. We can keep making progress. Well, what's kind of happening in this scenario is we tend to be doing non-blocking sends, non-blocking receives. By doing this, if we haven't got a response back, we can go and do some other work. We can be useful. We don't suspend everything and block what's going on. So we can be sort of more concurrent and we can make better progress. But I keep hearing, I almost feel like this is like a crybaby response now, but synchronous is so much easier. That's the way people will look at this sort of problem. I think it's an immaturity thing. You learn, how do you manage the feedback? How do you manage the state? How do you stop using the wrong technology to solve a problem? Like the fact that we're using a document fetching protocol to make what are requests that are messaging. It's a very different sort of thing. So if we start thinking events, but also start being aware that the world is distributed, and it's distributed in space and time. And we have to acknowledge this. This is the part of the growing up and being an adult and not being a crybaby and having the protocols of society is we take some responsibility and we deal with it. Then we can get through there. What can we do in the meantime? Well, if you're going to design your own APIs, design them as asynchronous and then wrap them with synchronous for the people who haven't quite grown up yet. So it's a bit like it's giving a drug addict methadone. So you can kind of keep them going for a while until you sort them out with a better way of working. And by trying to go asynchronous, we can do a lot more in this space. Now the thing is, for many people, they don't even kind of know where to start in this because it's not something they're used to. If you had grown up in a world since the web existed, this asynchronous world is so alien, but that's how things used to work. If you work in embedded controllers, you work in networking, you work in anything else previous to the web, it was the natural way of working. We just have been now conditioned into some kind of dodgy ways of thinking. And so we kind of think we build RPC on HTTP these days. We built that over TCP, but it shows a lot of problems. We're trying to fix this lower down in the stack. So TCP, we end up with three-way handshake to just open a connection. So we send an ACK across, we get a SYN ACK back, we get an ACK from that. That's a lot of round trips just to get the connection open. So then we move to things like TCP fast open, where we'll use a cookie and we'll save one of those directions across there. And then we're evolving now to protocols like Quick, where we're using UDP. So if you're using a Google service now in a Chrome browser talking to a Google backend, you don't use TCP anymore, you're using UDP over Quick. Like, we've learned some of this along the way. So HTTP1, so we went through Speedy, we go through HTTP2, and so we're trying to make this more asynchronous, we're trying to deal with things, but we're also making mistakes. I had a good conversation with Simone last night, and he was pointing out that in HTTP3, but we didn't ask the fundamental question, what can go wrong? What if that breaks? Then we've lost the ability to render any of the page because everything's tied up in the one connection. We need to be thinking about how do we deal with the what can go wrong. Again, that's the kind of growing up as an industry. We are seeing the growing up in some other places really nicely. Like, so TLS going from 1.2 to 1.3, that's a really nice maturity. If you read the detail of that spec, we've taken a lot of the complexity out of it. We've dealt with a lot of the issues. So it's more robust now. It's easier to understand. It's faster. Feel free to go read it. It's up there on the web. It's there. It's kind of interesting. Another big subject that kind of fits with a lot of this. So once you start going asynchronous, the big option open to you is batching. And if you stay in the synchronous world, you can't batch cleanly. And again, for me, this comes back to etiquette and behavior. So imagine you go around to a friend's house, and they're making you dinner. And you arrive at your friend's house for dinner, and they say, do you know what? I need milk. Could you please go to the shop and get me some milk whilst I'm doing the rest? And they go do that. And you think, yeah, this is a good friend. I'll happily go do that. So you go off, you go down to the shop, you come back again. And you give them the milk, and they go, do you know what? I actually need more milk. Could you go to the shop again and get me some more milk? So you go to the shop again. It's a good friend. You keep doing this. You bring back the milk again. They come back and go, do you know what? I actually need more milk, and I need some cheese. And at this stage, you start thinking, this is starting to border on being rude. They're not considering, like, you've invited me around to your house, but I'm not actually sitting around with you, having good conversation, enjoying the food, having some wine. I'm running backwards and forwards to the shop. So you wouldn't do this to a person, yet we do this to computers. And it's not saying that computers have feelings, but it shows you how when we disassociate, we don't think about what we're doing so much. And this is where a lot of the problems comes in some of our design. If we use some of our sort of inbuilt feelings at how we deal with stuff, we can design stuff that's much more efficient. So, and this is going to get very real. So as we go to things like 100 gigabit Ethernet, we cannot interact with it in the way we have been so far. The BSD sockets API will not let us drive traffic at that sort of rates. We need to be more efficient and batch across. Because syscalls is actually at the core of this. The cost of a system call is really significant and getting worse, not getting better. So things like Spectre and Meltdown have increased the cost of our system calls. So we need to do them in a much more efficient manner. We have examples. So things like in Linux, we can use send a message, receive a message. So we can send multiple messages and receive multiple messages at the same time. So it's like go down to the shop and get me 3 pints of milk rather than just go down and get me one at a time. And so you deal differently. We're also moving APIs to our user space. So onload VMA. We're seeing this with DPDK. These are all APIs that you see people using in the high performance space because you can drive at extremely high throughputs, extremely low latency. But the protocols are so different to how we react. And by using some of these, what we can do is we can just naturally batch up and we show some mechanical sympathy for dealing with something. So it's like, just think about what you're doing. Like everything you do has got consequences. Realize how do you use things in an efficient manner. Don't waste. I think another great example is ORMs. ORMs in SQL. So it's basically, I'm an OO program and I'm going to make you work the way I want you to work, Mr. Database. You actually think about it, it's bloody rude. It's like, it's not designed to work. It's sort of, the database, I'm brilliant at set theory and you're making me do OOO. I can do joins really, really well. Instead, you pull out this table and you pull out that table and pull it all across and then you put it back together again. It's like, you're just not respecting what I'm good at. It is interesting when you start thinking at this sort of level. I think it even goes further up the stack. You start to see some kind of interesting, weird behaviors out of people. I kind of call snake oil protocols. Two-phase commit and XA is one of the best examples of this. And it's all about, I don't want to know. This is somebody else's problem. They're not going to be the grown-up, they're going to be the crybaby and make the problem all someone else's. But they're not dealing with the what can go wrong. In fact, there's some really serious what can go wrong issues in two-phase commit. In fact, it's proven to be a protocol that is broken, yet we still keep getting it peddled. And the reason it got peddled so much is large corporations said, don't worry, we'll take care of all of your problems if you buy our product. And this is the kind of classic silver bullet thinking gets us into that, no, sorry, you some responsibility you got to take in this. Like a great paper back from 2004, Jim Gray and Leslie Lamport. Unfortunately, we don't have Jim anymore. But it's got some great quotes in this research about how broken two-phase commit is and how there's better ways of doing this. Like, here's one of the quotes. Two-phase commit is not fault tolerant because they use a single coordinator whose failure can cause the protocol to block. It's got a single point of failure in it. And do people think that two-phase commit takes away all of their problems? They should read the heuristics part of the spec if they really believe that. You're not absolved from it. You just kind of pretend. This is common in many protocols that require arbitration, where basically you're deferring to a third-party responsibility for sorting stuff out. It's like everything should be done via lawyers, rather than sort of realizing things can be done by coordination and done in a really nice way. Some of the best protocols deal with things by consensus, by collaboration. I showed the example with the multicast stuff, using random timers. Much, much better than sort of command and control type things. I see this like promises around, we'll give you guaranteed delivery. That's another one. I'm sort of putting a trademark on this. Like, the number of times I have seen this over the years, and it is so broken. Seriously, anybody tells you they can do guaranteed delivery, you can just sort of go, snake oil salesman, run away from them. Because it is such a bad thing to keep claiming. Because at a high level, we should have feedback. Like, Claude Shannon's original work in information theory, he pointed out one of the most fundamental things in information theory is feedback. You've got to take responsibility for knowing that you've communicated correctly and having feedback. So imagine going in, seeing your loved one at home and saying, I would like you to do this, and you sort of say it in a mumbled or an unsure way, and they don't quite understand you. And then later it doesn't happen, and you have an argument about it not being done. I'm sure many couples will understand this thing quite well. Where it's like, you ask for something, and then you check that you've got understanding correct. And you check along the way to see, like, is everything okay? Is there anything I can do to help out? That is a good feedback interaction cycle. You can achieve much better things through that, rather than throw it over the fence, blame somebody else later when it doesn't happen. That's what we do so often when we design our protocols. That's what makes them fragile. That's why they don't work. And once we start doing this in a sensible way, we can build it up in layers. And these layers can encapsulate other levels of protocol, and then we can rely on those because they give us certain behavior. But the important thing is, we got to depend on the behavior, not the implementation. Like, great example in tests, I see lots of tests that assert the internal implementation and not the behavior. If you do that, you can't refactor. Because refactoring is about making a change so you've got behavioral preserving change and stuff, not asserting the actual implementation. So, let's wrap up. I'm going to go back to are protocols the most significant thing in sort of human history that we have got for? Anybody understand this protocol? Recognize it? Yes, scientific method. Going right back to Francis Bacon, popularized by Isaac Newton and others. We're actually going to have sort of critical thinking about things. This enables us to do things at a level that we have not done before. And we build upon stuff. Like, we can end up with really cool things like another very cool photograph. So we've got a cool photograph this week of a black hole. We also got this one back in time, known as photograph 51. Work originally of Rosalind Franklin on understanding DNA. And it was all about, we had a hypothesis for what DNA was and how it worked. And if it worked in a certain way, it would have a helical structure. And if it had a helical structure, what is the experiment we can have to prove that? Well, if we use X-ray diffraction, it should show in a photograph to have the shape of an X. And therefore, we got it. So we end up following the protocols, we end up with a great result. Right, science has gone so far, protocols have got much more mature. We can get into single blind, double blind, triple blind, all sorts of really interesting things that are in there. So it gets to be a great way to learn from a lot of this. I kind of would like to ask, why are protocols not studied and practiced more when they're just so fundamental? They are in other disciplines. I don't see them practiced that much in our discipline, which is kind of the usual sign of like, we're kind of working it out as we go. So here's something to think about. On your next project, the first thing that you do you just install all your favorite frameworks and all of your favorite tools? Or do you actually start working out what are the protocols of interaction and talk to customers and work out what you should be doing, not what tools you're going to play with, not going to just go and do resume-driven development. So think about what are the interactions, because then it gets a whole lot easier. And it shows in other places, like the Golden Rule is a brilliant example of code of conduct. It's shown up across many different cultures, many different religions. It's like you do unto others as you'd like them to do to you. You think about things like that. This happens in systems. Think about your code. Do you write code thinking what it's going to be like for the person who's going to come along and maintain it? That person's probably you in 6 months. When you go back and you look at it, you go, what have I written? Why did I make this so hard? Thinking about that interaction. There's interactions appear all of the time. And if interaction's the main thing you consider, you can drive a lot of better behaviors. And on that, I'll thank you very much and leave you with a quote from Leslie Lamport, who started a lot of this stuff in computing. Maybe time? Time for a few questions, I think. No questions? I didn't show curly brackets, so no one's interested.
I guess maybe one opinion, if you have read the works of Mark Burgess on promise theory. Do you know about that?
I'm a little bit aware of it, but I haven't read it in any great detail.
Okay. Do you have any opinion on that kind of work?
I don't know it well enough to have an opinion. Okay. Thank you all.